So let's pick up where we left in the morning. So this wavelet transform that I explained is a key point. How are we going to analyze these noisy stochastic signals that we are putting through our systems? The only thing what we have to define, the only parameter, not parameter, the only choice, the design choice that one has to make is the selection of this function, or so to speak, this one. And it is called a mother wavelet. And this function is the cornerstone of this transformation. It should be such that allows this orthogonal transformation and stuff like that. However, we don't have to invent this function by ourselves. There are several candidates from which we can choose, and each of these candidates have some one or two parameters that we have to set before applying the transform. And based on these parameters, we can tune the precision of the transformation. So in the next couple of slides, I'm going to explain you in a nutshell how these parameters influence the behavior of the mother wavelet. So there is one key requirement that we have to satisfy. Because we are looking at impedance, we are not looking just at amplitude of the signal, but we would like to know its phase. The phase is actually more important in our case than the amplitude itself. So in order to get amplitude and phase, the possible choices of mother wavelets are only complex ones. So this C function, the mother wavelet function, the red one, can be real, or as in this figure, it can be complex one. So we are only looking at complex wavelets. And luckily for us, there are not so many of them. I'm going to go only to 2 of those. And all the analysis is done only by 1. Because as I'm going to show, it has really, really nice properties in low frequency range. And that choice has only 2 parameters. And I'm going to explain how these parameters can influence our impedance results. Okay, so the choice of mother wavelet is this function C. And what are we going to look throughout all these equations are these indexes U and S. U means translation in time. Translation in time. And S means contraction. Contraction, and it is called scale of the wavelet. So there is, if you open any wavelet book, there will be the title of the book, most probably, or the text will be time frequency analysis. So this is time, but throughout the text, you will never see a word frequency. You are always going to look for a word called scale. So wavelet transform as such doesn't have a notion of frequency. So this makes the whole situation rather pointless. We are interested in frequency, but there is no frequency, so to speak. So how do we, the key thing, what we have to realize is that for each choice of this function, mother wavelet, there is a transformation, how we can go from S to frequency. And when we draw this function, there is time on x-axis and scale on y-axis. And we have an additional simple transformation, how to transform this S to F. And all these things I'm going to explain now, just to have an idea. And if you ever read any wavelet book, just to know that they are going to talk about scales constantly, and it is assumed that you will know how to convert scales to frequencies. Okay, so unlike short-time Fourier transform, where we had things like this, a signal, whatever it is, and then we have windows, and we overlap them or didn't, we could easily transform back and forth between the frequency domain and the time domain. Such a transformation is not so straightforward with continuous wavelet transform, but luckily for us, we will never do the inverse form. And there is one other thing. If we require from the mother wavelet its integral to be 0, this reconstruction becomes quite easy. So these are just like bullet points, just to have them in your mind. All of this is already pre-programmed, and more or less every wavelet that we are going to use satisfies this condition, so you don't have to worry about it. If you read any book, you will be constantly bombarded with this integral. Just say, yes, yes, I know that this condition must be satisfied. It is, let's forget about it for the time being. Okay, so there is one particular thing that we are going to use over and over again. The wavelet that we are going to use in our analysis doesn't have a closed form solution in time domain. It is defined only in frequency. And as I'm going to tell you in a couple of slides, the implementation of the wavelet transform, actually the solution of this integral, is far easier and computationally more efficient to be solved in a frequency domain. That is why almost always we would like to know the Fourier transform of our wavelet. Since we know the choice of this wavelet function in a closed form, in a symbolic way, we can derive its frequency transform. And then by using simple Fourier transform rules, the scaling becomes multiplication here, and the translation becomes multiplication. These are simple Fourier transform tabular rules. If you know them, okay. If you don't know them, you don't have to worry about it. It is implemented in the code. It's a one-line implementation. I'm going to show it. These slides are just here for your like skeleton background noise, background knowledge, just to know what is happening. Okay, so what we would like to do now is, if we select a wavelet, when we were selecting a window, based on the window length, delta t, we could easily calculate what was its frequency resolution. In the wavelet transform, this is not clearly visible. So we would like to say, okay, we have a complex wavelet, and I'm going to draw it as I'm looking it from above. So we have a real and imaginary axis, and the wavelet has some shape. If I look it from above, there's a contour plot. And what I would like to know is, what is this width? And what is this width in the time domain? And if I do it in the frequency domain, then the wavelet will have some Fourier spectrum, and I would like to know this delta f. Why? Because these red dots define the dimensions of these rectangles. So when I squeeze it, I get really low delta T, but I have to somehow estimate how much is this delta F. And if I expand it, again, I can easily find this, but I have to find this small delta F. And how can we calculate this? Again, I'm just giving you this an overview. You will never, when doing numerical calculation, you will never look at these integrals. I'm just putting them because in a couple of slides, I'm just going to reference this parameter changes the time spread, this parameter changes the frequency spread, so that you will know what I'm talking about. How are we doing this? If you remember from any introductory course in statistics, if we would like to find a mean value of a random variable, the mean value is integral x times p of x dx. So this is the mean value definition. And we are using the same thing over here. So we are taking the modulus of our wavelet, and since it is a complex function, we do it absolute value over square, and we would like to find its spread in the time domain. A simple formula, and then we can what we realize, the spread is changing according to scale plus how we are moving it left or right. Okay, this is maybe a little bit cumbersome, but just look at it like this. Let me find better. So if I do it like this, we have time and we have scale here. And the higher the scale, the lower the scale, this is scale equal to, which is equals to high frequency. And this is scale equal to some maximum value. It's inverted. It's low frequency, low frequency. So we say that the time of the spread is S times the spread of the mother wave. So this means that on lower frequencies, this spread is bigger. On higher frequency, because S is lower, the spread in the time domain is shorter. As this grid that I was working around. Exactly the same thing can be done for the frequency domain using the same derivation. So in that case, we can find now the vertical spread here and here. So these are the integrals. I will not go through it. You have them here as a reference. Whenever you open a wavelet textbook, there will be huge concentration on these relations because they have to derive it really, really carefully. We are not interested here at that. Okay, so these are the final relations. So we say in the frequency domain, the spread is inverse to the scale, as we saw. Since as we go up, so this is S maximum, this is S minimum, and the spread here is big, the spread here is small, because it is inverse, and so on. So now we have to find out how choice of the mother wavelet influences our behavior of the transformation. The goal is to somehow define this grid, to define this and this. We are not going to look at the grid per se, but we must know how the choice of our parameters changes the shape of this grid. That is the takeaway. There will be two parameters that we are going to talk about, beta and gamma, and I'm going to explain what these values mean. Just put it in your mind that the selection of these beta and gamma changes the shapes of these rectangles, the width and the height. That's it. The previous integrals prove that they do this. Let's say that this is okay. So now we would like to implement this. So we have our signals measured, and we need to calculate these integrals numerically. We will not be able to solve it symbolically, because we do not have symbolic values for our data, because they are corrupted by noise. We have to do it symbolically. We have to do it numerically. How are we doing this? So the wavelet transform is it's not a convolution. It's not a convolution, but it's this integral. I'm not going to discuss what kind of form it is. It is this integral. Solving it in the frequency, in the time domain, is a little bit problematic. We can use trapezoidal integration and stuff like that, but we can easily do it in the frequency domain. Why we can do it? Because of one fundamental theorem in wavelet transform, which says if I have two functions in time domain, f of t, and I do star, I will tell what the star is, g of t, this star is convolution, and this convolution is actually this integral, minus t f tau g t minus tau d. This integral in the time domain is actually Fourier transform of f times simple multiplication Fourier transform of g. So I can easily transform this integral into two multiplications in the Fourier domain. Plus, as I told you a couple of slides previously, because we select the mother wavelet, we know its shape in a symbolic form. We can calculate its Fourier transform symbolically. We will do it once. Actually, none of us will be doing it, because we know the Fourier transform of the wavelet up front. So this is known. All we have to do is take the signals that we measure, calculate Fourier transform of the measured signal, multiply it by a known wavelet, and do one inverse Fourier transform to get back to the time. And all the talking that I was doing this morning to now, this 10 minutes or something, boils down to this. All we have to do is take a Fourier transform of our signal. We know the Fourier transform of our wavelet, multiply them. So just to get an idea, what are we going to do? So we have our signal like a vector. Sample 1, sample 2, and so on and so on. Call fast Fourier transform in whatever program you are using, and you are going to get sample 1 in Fourier domain, sample 2, sample n. Then we know our wavelet. We already have it. We have this wavelet matrix, and we multiply this with this, like simple multiplication. And the resulting multiplication, we do inverse Fourier transform, and we get the actual result, which is called continuous. So let's see the complexity of this approach. Fast Fourier transform has complexity n log n, and inverse Fourier transform has complexity n log n. If you are not familiar with complexity of algorithms, it shows us how many operations a computer should do in order to perform that operation. And one would say, okay, why is this n log n so important? So just to give you an idea of what I'm talking about, I'm going to put one more slide here as a whiteboard, as usual. So if we usually if we usually have something like this, we would like to multiply two vectors. We usually do something like this: for I equals from 0 to n, for j equals 0 to m, for example, multiply a of a times b of j, whatever. And these are for two loops. Complexity of this algorithm is m squared. So if n, and m are really, really big numbers, we can say that they're both like some really big number n. So we will have to do n square multiplications. This line will be called n squared time, and then we will calculate everything. So you're going to say, okay, fine, n squared, who cares? A million to the power of 2 is 10 to the power of 12. We have a gazillion gigahertz chip, so what's nothing? Why are we bothering with this? Well, if we plot a function n squared versus how n log n looks, we will see that this n squared rises extremely faster than n log n, which means that this implementation is extremely more computationally efficient. So if I go back here, solving this integral using trapezoidal integration would be complexity n squared. Doing this trick, we are doing complexity n log n. So we are doing exactly the same thing, extremely more efficient. This means that we need less computational power. We can use really, really, really cheap chips for on-board implementation. Now I'm again crossing the line from a laboratory to a practical implementation. And we are not losing even a single drop of accuracy. Everything is preserved, but we did everything extremely, extremely efficient. So now we have, I gave you a way how to generate the signals, how to calculate this continuous wavelet transform. The only thing what is left is to select this wavelet function, and we are done. So let's look at this. We are going to look through two choices. The top one is called Morle wavelet, and the bottom one is called Morse wavelet. These are their representation in complex domain. The Morle wavelet is also known as a Mexican hat wave. Why are we saying it? So it is a sinusoidal signal modulated by this function. And because this is in real domain, and the same thing happens in the imaginary domain, if you see it from the top, it looks like a sombrero. Then why it's called Mexican hat wave. And there is another one called Morse wavelet, which we are going to use in our implementation. And the choice of these wavelets have profound implications in low frequencies. So if you do battery analysis, you should most certainly use the Morse wavelet. Practically, we are using only Morse wavelet. And I'm going to explain now why such a small change has such profound influence on the final results. So this is a takeaway note. Now we are going really deep. You can go to sleep in 6-7 slides. I will wake up. We have to go through this. I will not. This is the most problematic part of my presentation. I was unable to do this in a comic book style, so I apologize up front. Bear with me, I will wake you up. Okay, so this Mexican hat wavelet has this formula in the time domain. It is complex, and from this formula, you cannot see where the hell are those two sine waves and where the hell is the Mexican hat thing. In order to look at this, you have to always say that this is actually, if I do Euler formula, Ej theta, this is cosine theta plus j or minus j sine theta. And this is where the two sine and cosine came out hidden in a complex way. So one is on the real axis, one is on the imaginary axis, and then we have this exponential decay on both sides. So it's a really peculiar shape of drawing a Mexican sombrero. So in this wavelet, in this formula, there is only one parameter, and this is this omega zero. This is really important. What this omega zero actually says, if we look at this part here, it actually says what is the frequency of these sine and cosine signals that are in the Mexican sombrero. So if we have omega equal to 10, then we will have, I'm going to draw it like this. So, and this is the sombrero. And then we have 10 hertz signal going like this. And if this omega is 1, then we, let's draw it true, it will be like this. So we can actually set how many stringings of this will be in our wavelet. And why is this important? Well, imagine if I have the red one with very, very little oscillations inside. If I want to find high frequency component, I will have to squeeze this red thing really, really, really tight. But when I start squeezing it in time domain, because of this Heisenberg principle of uncertainty, the frequency domain will start to spread out, as if, imagine that this has to be always like a rectangle with constant area. So if I start squeezing it from the time domain, it will start to expand in the frequency domain. But if I take the blue wavelet with more oscillations inside, in order to get into the higher frequency, I don't have to squeeze it that much. But in the low frequencies, I have to expand it so long that in order to find really low frequencies. So this is the trade-off when you are going how to select this omega. And you can change it. You can do low frequencies with the red wavelet and high frequency with the blue wavelet. Everything is legal. You can do this change. Because, why we can do it? Because we are not recreating the single deck. Okay, so this is where those integrals that I jumped over are coming into effect. And this was the comic book representation of those integrals. And now the solution of those integrals, if I pop this mother wavelet inside. So you have the solutions here. I'm not going through them. Go if you like. What they're going to tell you is that if you squeeze it, it will pop up vertically, and how much it pops up depends on this selection of omega zero. Nothing else. That's the only thing what they're telling you. They're there. Look at them if you want. Jump if you don't want. And again, this is the properties in the frequency domain. So they're nice looking integrals visually. I don't know. I'm not going into them. I don't want to do it. So the major thing what we would like to know now is how to go from this scale to frequency. And in the Morley wavelet, this omega is the one thing that transfers, because this omega shows how many wiggles there is in the wavelet. And if I take the red wavelet, the S will be, so just to draw it, let's draw it like this. So if this is time and this is scale or frequency, if I use the red wavelet on scale 10, there will be frequency, I don't know, 5. On scale 2, on scale 1, there will be frequency 0, 1. But if I use the blue wavelet, on scale 10, I will have 50. On scale 1, I will have 1. So actually, the wiggles inside changes the frequency where I'm doing the analysis. And this is the transformation. Everything is implemented inside. You don't have to look at it. But what you're going to get is, when you start my script and you say parameter omega 0 is 5, the result will give you impedance in some frequencies. And when you change parameter omega 0 to 1, it will give you results in different frequencies. As if, and the bizarre of it will be, when we always draw frequencies, we calculate in these fixed points. And we think that these fixed points we are selecting, we have 1, 10, whatever frequencies we use. Here, the calculated frequencies depend on the wavelet that you use. You cannot shot at every possible frequency. You can select only a vast majority of them, but they will change based on the values that you use. So the red wavelet will give you these frequencies, and the blue wavelet will give a little bit different frequencies. The ice curve will look the same, but the points where the ice curve was calculated will be slightly different, because on each scale, because wavelets are calculated in scales. So scale 1 for the red wavelet is frequency 1 Hertz, and for the blue wavelet is 5 Hertz. That is the effect that you're going to get. But when we are doing long-term experiments, we select one wavelet and we say, okay, this is our tool, and we are going to calculate every ice with the same tool, and all the points will be on top of each other. But if you start changing it, they will start to wiggle back and forth. That's the effect, what you're going to get. And how do we go from frequency to scale? In this Morley wavelet, this is really simple. So omega is actually S times omega 0. And this is the case. S stays constant, but if we change this omega 0, we're actually changing here. That is it. That is the only thing what you have to know. So there is one more thing that is really, really, really important. It's called analyticity of the wavelet. So in complex analysis, analytic function is a function that has only positive frequencies in the frequency domain, which means that if I have a function f of x, and if I do a Fourier transform, then the Fourier transform will have positive frequencies and negative frequencies. And usually when we have real functions, the spectrum is symmetrical. But if I have a complex function on this time, in the time domain, and when I go to the frequency domain, this spectrum doesn't have to be symmetrical. So we have analytical functions are those functions that are zero in the negative domain. So fine, who cares? This is actually really, really, really important property. Why? Let's go to this equation. The equation that I told you that it was wrong yesterday, it was wrong this morning. This is the correct. We don't measure complex signals. In our real world, all signals are real. So when we calculate Fourier transform of our voltage and of our current, their corresponding Fourier spectrums are symmetrical. Regardless how do they look, spiky, non-spiky, nobody cares, they are symmetrical. So, okay, they are symmetrical. We have positive frequencies and we have equal negative frequencies. They are symmetrical. So when we do a Fourier transform, we are getting the positive frequency part and the negative frequency for the current, for the voltage, and for the currents. But when I did the division, I said, oh, look, I'm going to take only the positive parts, I'm going to divide it, and we are done. But what I did actually was, by doing so, I said, look, all the negative frequencies, I will make them 0. So I do FFT, and I take the half of the matrix and I put it to 0. But if I do inverse of that, I won't get my measured voltage. I will get a complex signal. And by doing so, we can only do ICE if the signals are analytical, if they have only positive frequencies. And this becomes quite apparent when we come to low frequency signals. I'm going to draw it. New slide. I have to draw it. So imagine the following scenario. We are doing ICE calculation at a very, very low frequency range. For example, batteries. We would like to go to 1 millihertz or 800 microhertz, really, really low. So we are doing, oh, sorry. So let's do it like this. This is the frequency domain. And if we do not have, and we have, let's say that we have a sine signal that is really, really low. It has amplitudes on both sides, positive and negative. And if I draw its phase, let's do it here. So this is amplitude, and this is phase over frequency. So the phase here is, I don't know, something, it goes like this, but on the other side, it goes like this. So it flips. It's symmetrical. So if I now take my wavelets in the frequency domain, and my wavelet is not analytical, what does this mean? It means that it has positive frequencies, but it has some negative frequencies too. And I want to calculate the impedance. I will say, what's the amplitude here? Well, the amplitude on the positive side and on the negative side is the same. So I don't make any mistakes. So I can calculate this freely fine. But when I jump to the base, to the phase, my wavelet has these characteristics. So it will say, what's the amplitude? The amplitude is, because it does the summing, integration, it will say the phase is plus x radians minus x radians. So the phase is 0, and the phase is not 0. And on the low frequency, we will get complete garbage. So that is why we want our window, in this case, our wavelet, for sure not to have negative frequencies. So when we start squeezing our wavelet really, really low, we don't want the wavelet to pass this line. It can do whatever it wants on this side, but for the love of God, it must not cross in the negative side. In that way, when we do it, we will not have this issue of making a mistake in alpha low frequencies. That is why we would like to have analytical wavelet. So if I put here analytical wavelet, somehow what it will do, it will just make this 0, and it will make this 0, and what I'm left of is the relations that I gave it to you yesterday and this morning with an equation sign, which wasn't true, because I said that I have a tool that is analytical and just cancels negative frequencies. And this is why is this important. So back to, I will jump a little bit further. So this is the Morley wavelet. This is the Morley wavelet when the frequency is 5 hertz. It's quite nice. Negative frequencies are down here. Everything is where it should be. And when I start pushing the wavelet lower and lower and lower, it tries to avoid negative frequencies. It's here. but it's unable. Some of its part goes below. And if I push it furthermore, this part becomes bigger and bigger. So Morley wavelet is not analytical. And if I push it really low, I will be unable to calculate impedance in the very low frequencies. So option number 2, Morse wavelet. Morse wavelet doesn't exist in closed form in the time domain. We only have its Fourier transform. But as I told you previously, this is the only thing what we need, because our implementation is one inverse Fourier transform of 2 multiplications of Fourier transform. One of those is this one. So perfect. Nobody cares how it looks in the time domain. Let's look how it looks in the frequency domain. Is it analytical? Well, this is the key part. It has this function. It says, if you go below 0, it's 0. If it goes above, it's 1. So we have this like a cutoff. This function never goes in negative frequencies. So how does it look when I start pushing it back? I will go back to slide. So this was the Morley wavelet, and this is the Morse. And as I squeeze it towards 0, it actually never jumps below 0. And this is why we can do really precise low frequency measurements. Everything what I have in the analysis is done using this wavelet called Morse wavelet. These are the time domain. This plot shows the time domain of the wavelet, how it looks. You can see the wiggles here. And this is how we select the omega. There are 2 parameters, beta and gamma. And with this beta and gamma, we select how many wiggles there are inside and so on and so on. And in every Python implementation, you will have to select what is beta, what is gamma. I am providing you default values of those. If you ask me how did I come by that, a little trial and error and stuff like that. We are currently working on algorithm that can optimally select the values based on your time signals. But from our experience, I provide potential candidates for these values so that you will have good quality results in the low and in the high frequency bands. So now, waking up from all these equations, this is the takeaway note. Whenever you hear that we need a function to be analytic, it means it cannot pass through negative frequencies. This is very, very important when we go towards low frequency range. And for that purpose, we are using Morse wavelet. So all this deep dive was to tell you, when you do this analysis, use Morse wavelet, trust me. So I hope now you trust me that's why we selected this. Next question is cone of influence. Now we're going back to comic book style approach. There is, if you've seen the figures that I'm drawing, I'm always drawing them like there is a signal only in like a cup-shaped form. The signal is here, and this here is kept white. So I have areas in the time domain where I cannot calculate this analysis. Why is it so? And as I said, in the low frequency range, I have to stretch this wavelet, this wiggly thing, as much as possible in order to make it to have very low frequencies. But when I stretch it, I make it longer in the time duration. So what happens is, imagine that I have a signal, and my signal exists only within this time. This is time 0, and this is, let's say, 1 second. I have a 1 second long signal. And I start to analyze it. I put a wavelet at time 0 because I want to see what's the value of the time frequency at the beginning. part of the wavelet is on the left side, part of the wavelet is on the right side. And when I try to calculate the integral, I need to multiply this part of the wavelet with something from the signal. I don't have a signal there. What should I multiply it with? Is it 0? Well, if I say that it is 0, imagine a signal like this. I have a sine wave like here, 1 second long, and it has some DC value. And then you're telling me, and we can say, okay, it's 0. This means that the signal is like this. And this jump is high frequency jump. So I will get some information that there are some high frequency parts here that actually do not exist. They exist because of my choice that there was a spike here. Okay, then we will say, look, why don't we say that it is a straight line? Okay, then if I zoom here, I might have something like this, straight line, and then sine like this, because I cut the sine when it was high up. And then again, I will have some high frequency parts here. So the only logical solution is to say the following. If I have a part of my wavelet outside of my observation window, I will not calculate the analysis. And this is the shaded area here. This is the place where we cannot calculate our wavelet transfer. And because this looks like a cone, it is called cone of influence. And the shape of this cone depends on the selection of the wavelet transfer, of the mother wave. And within our analysis, everywhere there is a selection. Do you want to select cone of influence or not? Why do we allow sometimes to calculate everything without a cone of influence? Because, as you can see here, because we have short signal, there are low frequency ranges where we cannot calculate it. The only way to calculate these low frequencies is to make this signal longer. And if we don't have that luxury, we can say, okay, we are going to make a mistake. We will pad the signal, and then we start to do some stuff just to get an idea what's happening down there. You should not do this. In our analysis, cone of influence is included by default. You have to go and uncheck it by yourself programmatically. I'm going to show you how, but this will affect the accuracy of the results, and this is why it happens. So this is a takeaway. Now the mathematics behind that is here. I'm not going to go through them. You have it. Go and check it if you want, and you should. This is a really, really important part, because if we don't include this cone of influence, what we are going to see is the influence of the edge effects. That's how it's called. Okay. So this is where we are now. So we done how we can generate stochastic signals, how we can save memory, how we can analyze these stochastic signals, but I never talked about the impedance. And we are talking almost 2 hours, and this topic was fast impedance analysis. We wiggled through a 2-year amount of material and no impedance measure. So this is where everything now comes together. And as you can see, this yellow part goes a little bit deeper, but luckily I can do it comic book style approach. So there is something, the impedance calculation that I'm using this statistical random signals is something that is based on a methodology called weighted overlap segment average, or WOSA, or WOSA. It is a approach developed around 1992 for system identification. If you write VOSA on Google, Gemini, ChatGPT, wherever you want, you will get a really, really deep insight analysis how it works. The takeaway note is that we are not doing a ratio of two Fourier signals, but we are using cross correlation of the signals. So this is what I'm going to show why it works. And this is where all the noisy stuff becomes together. This is the main part, and I think that we can do it comic book style. So we said that this is our impedance that we would like to look at. G of S, it should be Z of omega. I will change the notation. And this is our input, this random signal. This is our output, and this is the noise that we measured. And let's start with the analysis. So we say, okay, what is the cross correlation between the input and the output? So why are we looking at the cross correlation? Because input and output are correlated to our impedance value. And if you find how this cross correlation works, we will find our impedance values. So we say, I would like to calculate the cross correlation. By definition, the cross correlation is expected value of one signal multiplied by complex conjugate of the other signal in the frequency domain. Fine. Let's put this equation into here. So instead of y, we are putting our impedance times x. Let me do it. So I remove this part. So we put, instead of this y, we put this equation here, and this should be z. And we are having this. This part is here multiplied by this here. Then we solve this multiplication. We have this part is here plus this multiplication here. And because expectation operation is linear to plus and minus, just to give you an idea, if you don't have this in mind, expected value of x is equal x times the distribution of x dx. And if I ask what is x1 plus x2, it is integral of x1 plus x2 p of x. And this is integral x1 p over x plus integral x2 p of x. Here, this plus can go here and here. So this is what I do here. Is the noise of Mother Nature correlated to our signal? No. So these two signals are not correlated at all. So this is 0. And this is what I've been left. Our impedance is not unknown. It's there. It's not correlated to our signals. So we can take it out of the expectation value. And we have that, and we end up with this equation here. And at the end, we say our impedance is the ratio of cross correlation of the input and output and the autocorrelation of the input. And this is the way how everyone does impedance. No one is doing Fourier transform. All those Fourier transform slides are just for you to understand the basics of it. When they do numerical analysis, this is the way how we do impedance analysis. When plug Biologic or Tanner, they are putting sine signals, but they're not using FFT over FFT. They are using autocorrelation of one sine divided by cross correlation of those two sines. And I'm going to show you why it is like that. And where do our analysis comes to? We can calculate these correlations from the wavelength transfer. So we never do division, because if you remember last time when I told you, so this is it, We never do this. Never. Nobody does it. Although it's logical, everyone would do it like this. No one does it like this. And when I told you, let me find if I have, maybe I will do it like this. It's easier to jump back to this slide. When I told you that I have a wavelet transform of the current and wavelet transform of the voltage, and then we divide it somehow. We never divide it per se, because we have a lot of zeros here, and if we divide it, it will blow up. So what we do, we take these two vectors and calculate cross correlation. And this cross correlation is a multiplication. And if we multiply a lot of zeros, it will be 0. And then we sum them up because it's integral. Nothing blows up. Numerically, is everything stable? We do the same here as u, one according to the other. And then we divide these two signals. SYU divided SUU. And we get the impedance for all frequencies together. That's it. This is the final point. So we take wavelet and do cross correlation. We take wavelet and we do autocorrelation and divide these two. Numerically stable, there is no division by 0. And as I'm going to show you, it's noise stable. Okay, so this was the most difficult. We're out of the woods. Okay, so what does all this mean? Back to our original figure. We put this random signal through. We measured it with a noise. We measured it here with another noise. This is input, this is output. And we show that we never divide these signals. We calculate cross correlation and autocorrelation and divide those, and we get the impedance. But because we put stochastic input, and because we have noises everywhere, the impedance what we get, it's not a flat point. Even with sine waves, let's say that you have extremely precise measurements and you have all the time in the world. If you measure impedance repeatedly over in time, you will never get a single point. You will get a cluster of points. There is a noise in the measurement. But because we do analysis in such a way, we can actually derive the distribution of this measurement. How can we derive it? Whenever you go into this analysis, there is a really peculiar way of how we say how a stochastic signal looks. This is called a Kramer representation. It's really simple. As I told you previously, this thing here is a sine and cosine wave, right? And this thing here is random amplitude. We are saying that a stochastic signal is a cacophony of sine and cosine signals, each with different amplitude, as if we have an infinite amount of instruments in an orchestra and everybody is playing differently. What we are hearing is a noise, and this is a mathematical definition, and it's called Kramer representation. What is important by this Kramer representation? It says that no two frequencies are correlated. This means in the orchestra, there are no two instruments that are doing in the similar manner. Everybody is doing completely different. And why is this important? Well, if our signal that we are putting inside is such, because we generate it randomly, and we have in our signal two noise inputs. Noise when we generate it and noise when we measure it. Let's see how this noisy stuff influence the way how we do analysis. Because we have these random signals, we can calculate their cross correlation. And if we do it symbolically, we have the variance of the output, the variance of the input, and one parameter that is called correlation. And this says how one frequency of the input is correlated to the output. This is our impedance, because each frequency in our Nyquist curve, each frequency changes based on where it is. So if we can somehow identify this raw parameter, we have found everything. So how can we do it? Let's look at a case where we have noiseless signals. So again, we go through this analysis and we say, if we do a noiseless analysis, we can easily make the division. Which means that if we have noiseless analysis, we can do Fourier transform of the input, Fourier of the output, divide it, and that's it. We never have noises. If we have noise, this is what we are going to get. Let me find the proper one. No, here. If we have noise and do the Fourier transform, this one is the noise. And if we do some simple algebraic manipulation, we're going to get to this result. We have the impedance, because we divided two Fourier signals, plus some noise. But here we are dividing two Gaussian noises. And if we divide two Gaussian noises, we are getting something that is called Levi stable distributions. I'm going to write it. Levi stable distributions are a particularly nasty family of distributions. They have heavy tails. And because they have heavy tails, their variance is infinitely high. Which means that if I take a Fourier transform of my input and Fourier transform of my output and divide them, I will get my impedance plus infinite variance. So my impedance will be just a fuzzy mess. And it's not because you had the measurement issues, it's because of this effect here. That is why nobody is dividing. Nobody is dividing, although it looks nice. What we are going to do, what everyone is doing, is this, what I told you. We take the cross correlation and the autocorrelation. The noise is present everywhere. And if we go through this analysis, we get our impedance plus this value here. And what is important with this is this higher part. We have the expected value of the noise multiplied by the expected value of our voltage. What is the expected value? What is the mean value of surrounding noise? It's 0. So this means that this part converges faster to 0. And that is why we have to calculate the cross correlation versus the autocorrelation, because this converges extremely, extremely faster to the true value of the impedance. So yesterday, some of you in Seoul asked me, what about the noise? Yes, because we always think that we have to divide. If we divide and if we have a lot of noise, everything will explode. But we are never dividing. We are calculating cross correlation, dividing with autocorrelation. And because of the trick that you are looking at now, everything converges down. So it doesn't matter. In an idealist scenario, we don't even have to excite the system. We can just look at its output as if it is excited by noise, because everything will cancel out. And in long term, it will converge to our desired impedance. This is what I said now. It's rather bizarre, That is why we excited to increase our signal to noise ratio. But this is the trick what we are doing. Actually, everyone is doing everything. Everybody is doing like this. And regardless of the input, because of this, we can put broad spectrum input, go through this formula and get the complete impedance over all frequency ranges. The noises just cancel out each other. And when you see something like this presented, you will say, yeah, this looks everything nice, but does it really converge to zero? It does. That's why we are providing all the formula. So by having this, we can even derive the distribution of our Z, because now Z is not, because now we are working everything in the stochastic domain. Our impedance is not crisp value, it's stochastic. And these are, I have a derivation, you don't have to look at it. There are references inside. This is the PDF of the impedance as a complex, and this is the PDF of the real and imaginary components together. So what the hell is this? Let's draw it. These are real signals. So we measured impedance that is on the bottom left in the blue Nyquist plot, and one of the frequencies, I don't know which one, we took it out and we said, okay, because we calculate autocorrelation and cross-correlation, let's estimate the parameters of this formula. And the blue dots are our measurements. The red line is the actual fit of the above formula. And now we have the distribution for each of the impedances, and we can actually draw it here as a confidence interval. There are intervals where we are less confident because of low frequencies, bigger noise or whatever, and there are intervals where we are more confident. And we never draw a single line, especially in batteries. When you have this part here should be actually drawn like this. We have a measurement. This is the mean value. That is true, but the spread is this big. And when you compare it, when you compare these two values, if we have something like this change is not statistically significant. But because now we have this distribution, we can quantify it. We can say that, look, this impedance changed, but the change is within the noise levels that we have. We should not consider this as a fault, or at least with our instrumentation, we cannot. We need either more precise instruments, longer measurement time, whatever. With the constellation that we have, it is within expected values, and we can do this. So these are the formulas. This is their implementation. Nothing. And what we can do now, I'm now going back to my first two slides that I've started. I've shown you how we can generate these random signals. You can measure them, how we do wavelet transform, how we do confidence interval, and these are the parameters that we need to estimate the PDF. And as you can see, they depend only on the wavelet coefficients. And when we estimate this, we can just, the impedance pops out like this. There are no divisions, everything is numerically stable, nothing happens. And if I show you just these slides and say, trust me, you'll say, yes, okay, I've run it. It seems that it works. Why does it work? So today was like scratching on the surface why these shortcuts work. And now, the final implementation, as I told you, 2 Fourier transform and 1 inverse Fourier transform. This part here in the code is the implementation of the cone of influence. You can see it because you have all the code. And that's it. Let's see how it works. Let's see how it works. because I don't have a proper GPU, I will connect to my Slovenian computer. We'll do it remotely. Okay. So I'm going to restart the kernel just to be sure that nothing happens. Restart, and I'm going to right. So let's plot it. These are the signals. So the experiment is like this. We were running experiment. I think it's on a battery. I'm going to see what the result. I can't remember. But you have the data. What I have here is a time domain excitation signal and output. So we are exciting with noise, and this is the output with the current. You can see this is how the battery responded based on these changes. And we have noise levels here, and it's a little less noise here, but whatever. And we have excitations. Let me see bandwidth, let's say a bigger bandwidth, 100 hertz, so that you can see that it's a little bit bigger. So again, so we have these 6 sets of excitations, and then I will start the processing of everything that I showed you today with these lines of codes, and it's calculating impedance. So this is from 800 millihertz all the way to, I think, 1,000. And so 22 seconds, and this is the impedance that we get. These are real world signals, nothing is simulated. It is one LG battery, I can find which one it is. The gap here is placed deliberately because I chose a mother wavelet that is not so, that doesn't allow so many points in the low frequency. I put a lot of wiggles in the wavelet, and it starts stretching it out, and it starts losing places where it can calculate because of the cone of influence. That's why I have a gap. It doesn't mean that there is no data here. It means that with the mother wavelet that I use, I cannot calculate them reliably. I can just change the parameters and I will get different points, but the shape will stay the same. Or if I want to hide this, I don't draw points. I can just draw the line. Now it looks better, but actually everyone should draw it like this. And these are the frequency points where everything was calculated. It's logarithmically spaced, or if I do maybe better like this, and in y, this is the, so you see the gap here. It started on a very low frequency, and then I changed the wavelet, and it makes this bigger jump. Just to show you that the influence of the wavelet doesn't influence that much the shape, but it can influence the frequencies where it was calculated. But if we keep the same settings throughout our experiment, everything will be more or less the same. So I provide you here, this is an implementation in JAX, what I'm showing you here. It is in Python, the most numerically advanced implementation that can use GPUs as fast as possible. You have it in the repo, also MinPy implementation. It requires maybe twice amount of time to calculate all this stuff, but more or less the results are exactly the same.